Consider these two sets of objects. They look pretty different, right? In fact, they differ in every conceivable way. Their shapes and sizes, uses, materials and colors, and many more. But there is one thing that is common to both of them: quantity of items. Both sets contain exactly the same amount of items. This is the idea of numbers. Numbers are one of the most difficult concepts that mankind has ever developed. In a more precise terms, numbers can be defined as follows: one-to-one mappings of the elements of one set onto the elements of a second set creates an abstract idea entirely independent of the type or nature of the things in the one or other set, which expresses a property common to the both sets. This abstract property which we call number, and we say that these two sets contain the same number of elements. Imagine you just landed on this planet, you don't have a language, no idea of numbers, yet you need to count things. What do you do then? This is precisely the problem that our ancestors faced. In this video, I'll take you on a journey through time, unraveling how primitive civilizations first grasped the concept of number. Along the way, I will present archaeological evidence ensuring that it doesn't feel like a made-up story, rather a historical reconstruction based on concrete evidence. This is gonna be a long journey, so you better grab a cup of coffee and enjoy the show. In the dawn of human civilization, people wanted to quantify their world, whether it be the tally of their sheep or the toll of warriors lost in battle. The brightest minds of that era pondered over this problem and devised an ingenious solution. Let me explain it with an example. Imagine a shepherd in charge of a flock of sheep which is brought back to shelter every night in a cave. There are 55 sheep in this flock, but the shepherd doesn't know that he has 55 of them, since he does not know the number 55. All he knows is that he has many sheep. Even so, he wants to be sure that all his sheep are back in the cave each night. So he has an idea, the idea of a concrete device which prehistoric humanity used for many millennia. He sits at the mouth of his cave and lets the animals in one by one. He takes a pile of pebbles and moves on from the pile to the other side for every sheep that goes in. So without realizing the mathematical meaning of it, he has moved exactly 55 pebbles by the time the last animal is inside the cave. Now all he has to do is store this resulting pile of pebbles in a safe place. This way, the shepherd can check if any of his woolly friends are missing. Every time he comes back from grazing, he does the same routine, one pebble for one sheep. If he ends up with pebbles left over, he knows he has lost some sheep. No leftovers and everything's okay. Now if a cute little lamb joins the crew, he just adds another pebble to the pile. This is an example of a concrete counting method. All over the globe, people have used a variety of objects for this purpose: pebbles, seashells, pearls, heart fruit, knuckle bones, sticks, elephant teeth, coconuts, clay pellets, cocoa beans, even dried down. This easily manageable pile of pebbles essentially serves as a model collection and establishes a one-to-one correspondence with the flock of sheep. Remarkably, to this day, Muslims employ a similar device known as prayer beads to recite the 99 attributes of Allah subhanahu wa ta'ala. Archaeological evidence of ancient people used pebbles as counting tools is limited, primarily because pebbles are organic material that do not preserve oil over long periods of time. However, there are some indirect archaeological and historical clues that suggest the use of pebbles as counting devices by ancient civilizations. Some historical texts and ancient writings mention the use of pebbles for counting. For example, ancient Greek mathematicians like Pythagoras and Euclid are said to have used pebbles or small stones as counting aids. Another indirect evidence is that archaeological excavations at various sites have uncovered pebbles, shells, or other small objects that are potentially used for counting. For example, at the Tel Brak archaeological site in Syria, dating to around 4000 BC, large clay jars have been found containing grains, seeds, and other commodities. The arrangement of these items within the jars, along with accompanying cuneiform inscriptions, suggests that pebbles or markers are used to keep track of quantities and transactions. For relatively small calculations, ancient people frequently used their different body parts like fingers, wrist, elbow, shoulder, hip, toe, ankle, etc. as counting devices. Actually, people counted with things that were close to their hands, and nothing is closer to our hand than the hand itself. Human hand is a kind of natural instrument well suited for counting and elementary arithmetics. As we progress through our journey, we'll see that it has played a significant role in the evolution of number system. Archaeological evidence regarding people used fingers of their hands and feet is enormous. Due to time limitations, I will only provide a few of them. In the early language of Central Africa, 5 and 10 are respectively Moro and Mbauna. Moro is actually the word for hand, and Mbauna is a contraction of Moro and Bauna, meaning two. Thus, Mbauna means two hands. Here is another one. Lingua people of the Chaco, which is present Paraguay, use a set of number names broadly derived from specific number gestures. For the number 5, they use a word meaning one hand. For 6, they call wrist, other hand, one, and so on. Like Ali language in Api, a language spoken in New Hebrides, they call the number 5 Luna, literally means the hand. For 10, Lua Luna means two hands. In fact, archaeologists, historians, ethnologists, and philologists have come upon evidence of body counting at all times and in all regions of the world. In Polynesia, Oceania, Africa, Europe, ancient Mesopotamia, Egypt under the pharaohs, the Islamic world, China, India, the America before Columbus, and the Western world in the Middle Ages. Forget about the past. Even now at this modern age, I am sure as a child most of us learned counting and rudimentary arithmetical operations using our finger knuckles or joints. Muslims often use their finger knuckles as an alternative of prayer bead when it is not readily available. Another implicit evidence that people in the past used fingers of their hands and feet as counting devices comes from the fact that most of the number systems that have been used are 5 and 10 base systems, and some are 20 base. The concept of number base will be discussed in the later part of the video. For instance, languages that use base 5 or have traces of it in the number systems include Arawak, Carib, Serre, Fiola, Guarani, Wolof, Khmer, Hailu, Api, as well as some other African languages. The ethnic, geographical, and historical spread of base 10 is enormous, and we can say that it has become a virtually universal counting system. Here is a listing of the languages and peoples who have used a numbering system built on base 10. In the world today, base 10 is used by a multitude of languages. Here are some of them. Other civilizations preferred base 20, the vigesimal base. Amongst them, we find the Zapotecs and Maya of Mexico. Tamanas lived near the Orinoco, which is present in Venezuela, the Ainus in Japan, and the Inuits who lived near Greenland and Canada. The reason why a huge number of civilizations choose the number 5, 10, and 20 as the base of the number system is that most of us have 5 fingers in a hand, 10 in both hands, and 20 in total, including the feet. Body counting works well enough for representing numbers visually and immediately, but by its very nature, it cannot serve as a recording device. As crafts and trade developed within different communities and cultures, and as communication between them grew, people who had not yet imagined the tool of writing nonetheless needed to keep account of the things that they owned and of the state of their exchanges. Instead of using individual stones for each item, they turned to carving notches into bones, sticks, wood, and similar materials. These marked sticks and notched bones earned the name tally sticks. The word tally comes from Latin talia, meaning tweak or cutting. You will be surprised to hear that the British continued using tally sticks as a method of recording business transactions right up until 1829. Among the oldest and most widely found methods of counting is the use of marked bones. People must have made use of this long before they were able to count in any abstract way. Archaeologists have discovered hundreds of more recent tally sticks from the Middle East, Australasia, and Africa. Some were carved deer antlers or wolf bones, others were small tree branches. One of the most notable was the 22,000-year-old Ishango bone. It was a baboon's leg bone carved with notches. In 1937, archaeologists discovered a radius bone of a wolf marked with 55 notches in two series of groups of 5 at Dolní Bestonice in Czech Republic sediments, which have been dated as approximately 30,000 years old. The purpose of these notches remains mysterious, but this bone is one of the most ancient arithmetic documents to have come down to us. Even now, we sometimes use tallying, especially recording statistical data. Unlike our ancestors, we use pen and paper. Another worth mentioning system of numeration, which is far more advanced than tallying or pebble counting, used in Inca civilization, called quipu, which means knotted string. The device consists of a main piece of cord about 2 feet long onto which thinner colored strings were knotted in grooves. This counting device is an interesting one. Quipus are based on a fairly simple, strictly decimal positional system like our own. Again, you will learn about positional systems at the end of the video. Knots in different positions correspond to different digits in this system. Units are represented by the string being knotted a corresponding number of times around the first fixed position point, starting from the end or bottom of the string. Tens are represented similarly by the number of times the string was knotted around the second position point. The third point served for recording hundreds, the fourth for thousands, etc. To make it clear, consider the number 3243 as an example. To express 3243 on quipu, you knot the string 3 times at the first point, 4 times at the second, 2 times at the third, and 3 times at the fourth position point. Officers of the king, called quipu kamioks, meaning keepers of the knots, were appointed to each town, village, and district of the Inca Empire. Their job was to make and treat quipus as required. Even today, Native Americans in Bolivia and Peru use a very similar device, the shimpu, a direct descendant of the quipu. So far, we have considered 3 numbering systems which are more or less concrete in nature. That means we assign some physical objects like pebbles, notches in bones, or knots in ropes, etc. for things to be counted, which make a one-to-one correspondence between these two sets. These concrete numbering systems are only suitable for a relatively small set of objects. For larger sets, this method becomes cumbersome and hard to manipulate. Writing as a system enabling articulated speech to be recorded is beyond all doubt among the most potent intellectual tools of modern civilization. By recording speech in silent form, writing does not merely conserve it, but also stimulates thought. The earliest known writing appeared around 3000 BC in the land of Sumer, which lay in Lower Mesopotamia. Here also are developed the earliest agriculture, the earliest technology, the first town and cities by the Sumerians. As evidence of this, we have numerous documents known as tablets, which were used as a kind of paper by the inhabitants of this region. The ability to write enabled people to step up from concrete counting method to abstract numeration. Fundamentally, 2 principles can be applied for constructing number symbols. We may call them cardinal and ordinal systems. In the cardinal system, you just need to adopt a standard sign for the unit and repeat it as many times as there are units in the number. This is essentially a tallying system. The advantage of this system is you just need to memorize one symbol, which is quite easy, but on the other hand, for larger numbers, we have to write an insanely long string of symbols. Just think about the number 1 million. To write it down, we must repeat the symbol 1 million times. Ordinal is another possible extreme system. Here each number has its own unique symbol. Therefore, any number can be written just by using one sign. But for this to happen, we must remember an insane amount of symbols. In fact, in the first age of writing in Mesopotamia, Sumerians used graphical symbols to represent different material things. The total number of symbols used in this early stage of writing has been estimated to be about 2000. Here are few of them. Both of these extreme methods of numbering are impractical. To represent larger numbers, you can simply repeat the same symbol over and over again. Nor it is practical to create unique symbols for any number of numbers. To make any progress, people invented an ingenious method. They carefully choose a set of numbers as their starting point that can be easily managed by the human mind and assign a unique symbol for each of them. Then, following some defined rules, other numbers can be written using the chosen symbols. Different societies choose different sets of numbers as their starting point, assign different symbols to each of them, and define various rules for combinations. People used pictures, letters, dots, bars, etc. These symbols stood for numbers. They were carved in stone and clay. They are written on early forms of paper like papyrus. Now let's explore some ancient number systems to make this point clear. Ancient Egyptians used these pictures or symbols called hieroglyphs to represent numbers. Notice every symbol represents a value which is a multiple of 10. As I said before, this is because we have 10 fingers in 2 hands. They choose this as their set of fundamental numbers. Any other number can be written as a combination of these symbols and using these two simple rules only. The value of each symbol representing a number needs to be added. A symbol cannot be repeated more than 9 times. In case of 10 repeated symbols, next symbol must use. Let's look at an example. Number 462 can be written in Egyptian numerals like this. Here is another more familiar one, Roman number system. Romans use a combination of letters from the Latin alphabet to represent numbers. Here is their set of fundamental numbers. Notice that the first two numbers are unit and 5 and rest are a multiple of 10 of these two numbers. See once again how fingers in our hands shape the number systems. And regarding the rules, they follow both additive and subtractive approaches to form other numbers. Here are the rules for writing numbers in Roman system. I think everybody has some knowledge about how to write Roman numerals since still today we sometimes use them, especially when writing ordered list. Anyway, here are some examples. If you feel interested, check them out. One warning, never dare to do arithmetic operations using Roman numerals. One little task for you. These symbols are invalid. Try to find out which one violates which rule. Our last example is Hebrew and Greek numerals. The ancient Hebrew and Greek used their letters of alphabet for numeration system. They assigned a separate value to each letter of the alphabet. All of these number systems are 10 base in a sense that symbols are chosen for the numbers that are multiples of 10. Moreover, Hebrew and Greek have a unique symbol for the first 10 numbers and Romans only for the number 5. One thing that should be noted here is that base numbers that I mentioned here are not truly a base, because the concept of base arises in positional number systems. None of these systems are positional. We may call this pseudo-base. In the next section, I will discuss positionality. Before concluding this section, I think it should be emphasized that the concept of number and a symbol, that is to say conventional graphic signs that represent number concept, is completely different. The concept of number, which is unit, pair, triad, is absolute. On the other hand, a numeral is just one of the dresses that a number can have. You can change the way a number is written without changing the number concept at all. Numeration was a very important development of mankind. They allow us to advance from concrete plurality to abstract number. That is to say, operations on things to be replaced by the corresponding operation on number symbols. So far, we have made remarkable progress, but our journey is not finished yet. Let's write down a few numbers in different systems we have considered up to this point. Let's start with Egyptians. To write the number just 1 less than a million using Egyptian hieroglyphs, we need to use first 6 symbols repeating 9 times each. That is a total of 54 glyphs. Take next example from Greeks. Ancient Greeks wrote the number 7 on 755,875 like this. Let's break it down. Omega, Omicron and Epsilon denote the number 875. To represent higher values, lota was used as subscript. It increases the value of the letter by 1,000 times. For even higher numbers, Greeks adopt the letter mu, which comes from the Greek word Marias, meaning 10,000. Mu multiplies the preceding number by a factor of 10,000. As our final example, let's write this number in Roman numerals. As you can see, writing numbers in these systems arise all kinds of complexity. Although we can write 1 million just using one symbol in Egyptian system, but the preceding number requires a total of 54 symbols. A long string of symbols has already made our life difficult. On top of that, different modifiers like subscript, multiplier, top bar added another level of complexity, which makes arithmetic operations complicated. Forget about advanced mathematics. Even simple operations like multiplication, division of two numbers is extremely difficult. There is a story that I think is worth mentioning here. Around 15th century, while Europe was still using Roman numerals, a wealthy German merchant seeking to provide his son with a good business education. He consulted a learned man as to which European institution offered the best training. The expert said that if you only want him to be able to cope with addition and subtraction, then any French or German university will do. But if you are intent on your son going on to multiplication and division, and of course if he has that level of merit, then you will have to send him Italy. Such complicated operations only teach there. In our time, it is like someone graduating in arithmetic operations. In fact, people who could perform these operations were considered highly intellectual. This sounds funny. Now even a 6-year-old child can do such operations. This is because the number system we use today is highly systematic and we take it for granted. It took thousands of years for people to develop such an efficient system of numeration and the method for arithmetic operations. Now it's time to discuss positional number system. First, consider these 3 numerals from Egyptian system. Together they represent the number 111. But these 3 symbols can be arranged in 5 more different ways. In these 6 configurations, individual symbols don't change, and in Egyptian system represent the exact same number 111. But if we consider them as a whole, that is considering the relative positions, all of these arrangements are different and have the potential to represent 6 different numbers. The idea of positional system comes from here. To make this point clear, let's consider English language as an analogy. In modern languages, unique symbols are assigned for phonemes. Then different combinations of these phonemes produce different words. In English, we have 26 letters of alphabet, by which we represent more than 600,000 words. As an example, consider the letters A, E, S and T. 4 different arrangements of these letters represent 4 different English words. Now we can define positional system like this. If the value of a symbol depends not only on the symbol itself, but also on its position within the number where it is used, then this type of number system is known as positional systems. In this system, each place within a number is assigned a place value, which is an increasing power of a certain number called the base number. To work unambiguously, an n-based positional system must have n-1 different symbols to represent first n-1 numbers and the concept of 0 to indicate an empty place. Modern number system is a 10-base or decimal positional system. Before jumping into the modern system, let's discuss 2 ancient positional systems, namely Babylonian and Maya numeration systems. The first positional number system we find trace in history is the sexagesimal or 60-base system developed by the Babylonian, which is modern Iraq, around 1600 BC. Let's explore it in some detail. Babylonian used only 2 symbols, one for representing the unit and other one to represent 10. By grouping these 2 symbols, they produce other symbols for the numbers from 1 to 59, and this symbol stands for 0. Here are some examples. For numbers bigger than 59, positionality comes into play. For example, this combination of symbols represent the number 83,156. Notice value of each symbol is multiplied by the corresponding place value of that particular position. If, for example, symbols in the first and third positions are interchanged, the number will be changed to 201,923. If second place remained unoccupied, the number will be 201,623. But there still remained a mystery about the number 60. Though there is no clear evidence that why Babylonians chose to use such an unusual and big number 60 as the base of the number system, but one of the explanations that most historians accepted is that 60 is a highly composite number. A positive integer is said to be highly composite if it is divisible by a large number of factors. Number 60 has a total of 12 divisors, which makes it a convenient choice of base in many respects. In fact, the base 60 was and remains the preferred one in geometry and in astronomy to this day. A full circle composed of 360 degrees comes from the fact that a total of 6 equilateral triangles with sides equal to the radius of the circle can be fitted within it. Since Babylonians used 60 as the base of their number system, they took an angle of the equilateral triangle to be 60 degrees, which makes a full circle 360 degrees. For the very same reason, we subdivide a degree into 60 minutes and a minute into 60 seconds. Same goes for hours and minutes in timing. Another worth mentioning system that was used by Maya civilization of New Mexico is vigesimal or 20 base system. They also use two fundamental symbols, a dot represents unit and a bar represents 5, and combinations of these two produce the first 19 numbers. And this symbol played the role of 0 in their system. They wrote numbers from top to bottom. Here is an example. One thing that should be noted here is that in this early stage of numeration, 0 still wasn't considered a valid number, rather only a placeholder indicating an empty place within a number. There is a speciality about these two number systems. They are kind of composite systems in a sense that these systems use two bases, one as the actual base that plays the role of positionality, for Babylonian which was 60 and for Maya which was 20. But there is an intermediate base as well, which is not positional but used for producing other symbols required for positional system to work. The intermediate base for the Babylonian system is 10 and for Maya which is 5. Finally, let's talk about our own system. The number system we use today is commonly known as Indo-Arabic numerals, originally invented by Indian Hindus, then popularized by Arab Muslims. In Islamic Golden Age, Muslims realized the power of this numeration system, used extensively in their calculations. Finally, it was transmitted to the Western world. This is a 10-based positional system. It is a rich positional system in a sense that, unlike Babylonian and Maya, who relies on an intermediate pseudo-base to produce all the necessary symbols required, our decimal system uses 9 unique compact symbols to represent numbers from 1 to 9 and a symbol 0 for the unoccupied place. These symbols are called digits. In modern system, 0 is not just a placeholder, but rather a valid number in its own right. That is, we are allowed to use 0 in different arithmetic operations just like other numbers. 0 is a dangerous number. If multiplied by it, the number line collapses into a single point, and when divided by 0, all mathematical logics break down. That is, dividing by 0, you can prove anything you want. No other number possesses such power that 0 has. 0 has its own interesting story. You might be thinking, you have a story to tell about 0? This is also because we take its existence for granted. It took a very long time for people to accept void, nothingness, as a valid number. Maybe I will discuss it in another video. As I said earlier, in positional systems, each place within a number has a pre-specified value. For decimal system, it increases as integer powers of 10. That is, the first position has place value of just 1, second position 10, third 100 and so on. The same symbol can represent different values depending on its position. This is called place value. Let's make it clear through an example. If digit 2 takes the rightmost position, that is unit, then it will represent its digit value, which is 2. But if it occupies the second rightmost position, then its value will be multiplied by its place value, that is, now its value will become 20. For hundreds place, it will be 200 and so on. Now if you just write 2, what values does it carry? 2, 20 or 200? It's not clear because its position is not clearly defined. Here 0 comes into the picture and saves us. It makes a digit's position unambiguous by denoting that there is no digit here. This place is unoccupied. For example, without 0, 7 on 4 could possibly represent any of these numbers, which will certainly create confusion. Whenever we write a number in our decimal positional system, we write shorthand for a sum of powers of 10, each of which is multiplied by the value of a digit standing in the relevant place. Okay, that's all for now. I hope you have enjoyed this video. If you did, don't forget to like and share with others. Be absolutely sure to hit that subscribe button for more awe-inspiring scientific adventures. Until next time, keep exploring, stay curious.